Dear students, today I am giving the third video on compact spaces. Okay, we had last class we have started with the compact spaces. That is the first section of the first unit we have discussed so far. Now coming to the second part, that is compact spaces in detail. And we start with the theorem: every closed subset of a compact space is compact. See the proof. Let X be a compact space and let A be a closed subset of X. You have to prove that A is compact because A is a closed subset. And you take a cover, that is, let theta equal to set U alpha such that alpha in the index set be an open cover of A. What does it mean? That is, A is a subset of or equal to A subset or equal to union U alpha. That is the definition of the covering. You take another cover, that is, let's put theta dash equal to set U alpha, alpha in index set union X minus A you take. So then theta dash is an open cover of X, but X is compact and that the X is a finite subcover of theta dash. We call it as theta double dash. That is theta double dash of X. If X minus A is in theta double dash, then remove it. Then the remaining collection will be a finite subcover of A. That means A is compact. That proves the theorem. One remark is given, it's an important remark. A compact subset of a compact space need not be closed. A compact subset of a compact space need not be closed. Because earlier theorem, every closed subset of a compact space is compact. Now we are considering a compact subset of a compact space need not be closed. We can show it by using the following example. Example, consider R with finite complementary topology tau. That means R2 is compact. You consider Q is subset or equal to R. Let theta equal to set U alpha such that alpha index set be an open cover of Q. Then clearly Q is subset or equal to union U alpha where alpha in index set. Let U element of theta. That means R minus U is finite or R minus U intersection Q is finite. Since it is finite, you can take R minus U intersection Q equal to set a finite set, that is x1, x2, etc. xn. Let ui in theta be such that xi in ui for I equal to 1 to n. It's possible because theta is a cover of Q. Then Q is subset or equal to u1 union, u2 union, etc. union un. This implies Q is a compact subset of R. But Q is not a closed subset of R tau, because if Q is closed, then R minus Q is open. This implies R minus Q is finite. That shows Q is finite, which is a contradiction. This is the counter example. Next theorem. Let X tau be a Hausdorff space. Let A be a compact subset of X. You are taking a point, let P in X minus A. Then the X is disjoint open sets U and V such that A subset or equal to U and P element of V. You can discuss the proof. Let A be a compact subset of X. Given P element of X minus A, choose small x in A. That means never P can be equal to X or P not equal to X. X2 is Hausdorff. That is, X is Hausdorff is given. That means the X is disjoint open sets Ux and Vx such that the small x is an element of Ux and P is an element of Vx. The collection Ux such that x in A is an open cover of A, which implies A is subset or equal to union Ux, or x is in A. Since A is compact, we have x1, x2, etc. xn in A such that A is subset or equal to union uxi, that is union uxi, or that becomes a covering of A. You put capital U equal to union uxi, where I varies from 1 to n, and take V equal to intersection vxi, where I varies from 1 to n. Then U and V are open sets such that A subset or equal to U, and P is an element of V. Okay. So what is left to prove? It remains to prove that U and V are disjoint, or U intersection V equal to phi. If possible, take an element there, let Z in U intersection V. That means Z is in U and Z is in V, which implies what is U? U is union UXI. Therefore, Z is in union UXI and Z is in V means intersection VXI. That is, Z is in UXI for some I and Z is in VXI for all J. VXJ for all J. This implies Z is an element of UXI and Z is an element of VXI for a particular I. This implies Z is an element of UXI intersection VXI, which is a contradiction to the fact that UX and VX are disjoint. That means we get a contradiction, or U intersection V equal to phi, hence the proof. Next theorem, a compact subset of a Hausdorff space is closed. A compact subset of a Hausdorff space is closed. It's an important theorem. Proof, let X2 be a Hausdorff space. Let capital A be a compact subset of X to prove that A is closed. First take, if A equal to capital X itself, then A is closed. So take A not equal to X. That means A is subset of X but not equal to X. That implies X minus A is not equal to phi. So there is at least one pointer. You take that point as P. Let P is an element of X minus A. Here A is compact, and hence by the previous theorem there exists disjoint open sets U and V such that A subset or equal to U and P is an element of V. U intersection V equal to phi. This implies V is subset or equal to X minus U. Also A is subset or equal to U. This implies X minus U is a subset or equal to X minus A, which implies V is subset or equal to X minus U, which is subset or equal to X minus A. That means small p is an element of V which is subset or equal to X minus A. Here V is open. That means X minus A is open. That means A is closed. That is the proof. Next theorem. Let X2 be a compact Hausdorff space. A subset capital A of X is compact if and only if it is closed. We can discuss the proof. Suppose that A is compact, that means A is closed because X2 is Hausdorff. This implies A is compact. What is the reason? Since closed subset of a compact space is compact. So we can prove the result in that way. Next theorem. Let A and B be disjoint compact subsets of a Hausdorff space X2. Then there exists disjoint open sets U and V such that A subset or equal to U and B subset or equal to V. This result is important. We can discuss the proof of it. Let small x in A, that means X is an element of capital X minus B. Hence B is a compact subset of X and small x is an element of X minus B. Then by previous theorem there exists disjoint open sets Ux and Vx such that B is subset or equal to Vx and small x is an element of Ux. Now the collection. Now Ux such that x in A is an open cover of A. But A is compact. That means there is a finite subcollection. There is a disjoint. There exists elements x1, x2, etc. xn in A such that A is subset or equal to union Uxi. I varies from 1 to n. Put U equal to union Uxi. I varies from 1 to n. And V equal to intersection Vxi. I varies from 1 to n. Just like what we have done in the previous theorem. Then U and V are open sets and A subset or equal to U, B is subset or equal to V. What we have to prove? U and V are disjoint, or to prove that U intersection V equal to phi. If possible, take an element let Z in U intersection V. This implies Z in U and Z in V. This implies Z is an element of union Uxi and Z is an element of intersection Vxi. This implies Z is in Uxi for some I and Z is in Vxj for all j. That means Z is an element of Uxi intersection Vxi for some I, which is a contradiction. Therefore, we get U intersection V equal to phi. Hence the proof. Next theorem. Let A and B be disjoint closed sets in a compact Hausdorff space X2. Then there are disjoint open sets U and V such that A subset or equal to U and B subset or equal to V. You can discuss the proof because we are using the earlier results. Here A and B are compact sets. Why? Because closed subsets of a compact space are compact. Hence the result follows from the previous theorem. Next theorem is an important result. A continuous image of a compact space is compact. That is, compactness is preserved under continuous mappings. Continuous image of a compact space is compact. Proof. Let X2 be a compact space and YU be a topological space. We have to prove that YU is again compact because we construct in that way that f from x to y be a continuous onto function, that V alpha be an open cover of y, that is y is subset or equal to union V alpha. This implies f inverse V alpha is open in x for all alpha because each V alpha is open in y and f is continuous. That is, collection f inverse V alpha is an open cover of x, but x is compact. That means x has a finite subcovering. Therefore, the x is alpha 1, alpha 2, etc. alpha n such that capital X is subset or equal to f inverse V alpha 1 union f inverse V alpha 2 union etc. union f inverse V alpha n. You call it as result 1. This implies f of x is subset or equal to V alpha 1 in the union V alpha 2 union etc. union V alpha n. This implies what is fx? The y. This implies y is subset or equal to union V alpha I, our I varies from 1 to n. Or we get a finite subcovering for capital Y, or y is compact. A remark, that is, compactness is a topological property. Because f is a continuous mapping and under a continuous mapping, compactness is preserved, or compactness is a topological property which you can prove easily. Next theorem, the last theorem in this video. Let X2 be a compact space and YU be a Hausdorff space. Let f from x to y be a continuous function, then f is a closed map. You can use the results what we have proved here to prove this particular theorem, because proof we discuss that f from x to y be continuous and A is a closed subset of x. What does it mean? A is compact because x is compact and A is closed. But f is continuous. That means f of a is a compact subset of y, because compact is preserved under continuous mappings. Y is also implies f of a is closed. That again from the previous result. That means f is a closed map. That is, A is a closed set and f of A is again closed. That means f is a closed map. That is what the proof of the theorem. So we have given, or I have given here 7 pages notes for this particular video. Okay.